Okay, all right.
I should be doing engineering.
You're both honorary members of the media team, but don't let that go to your heads.
That's going to be tough. A lot of the media team, that's already happened to them.
That's oh man, I really walked into that one. All right,
Hostile
well,
interview.
hello and welcome to the pod. This is Roid Rage, episode 54. Permission to treat the guests as hostile. Permission granted. All right, we're joined this week by Max. Max, what is your title? What do you do here? I know you've been on the pod before, but in case we have some new viewers, and we're going to be talking about RF today, which we hit a big milestone.
Well, RF is what I do. That's my job. That's my title. I am AstroForge's RF engineer, one of very few. I hope that everyone watching this would know what RF is, but maybe that's just my twisted, fucked up brain that's been doing this for 6 years, I guess.
I think you do kind of have to have like wizard brain to do RF.
You do not. But that's a big misconception. Is even an idiot like me can get my hands on it. RF stands for radio frequency. So anything that you send from your phone up to the cell towers, that's radio frequency. Anything higher than that, that's radio frequency. Eventually, you start to get into light frequency, or they call it terahertz, because a hertz is 1 cycle per second. We can get into it later. I like what I do.
All right, we're also joined by Chris. Chris, what do you do here at AstroForge?
Yeah, so I'm Chris. I'm on the flight software team.
You don't need to hold the mic, buddy.
Skip. All right. Well, I'm Chris. I don't hold the mic. I'm on the flight software team. So I work on a variety of different things. But one of the things that I've been spending a lot of time on recently with Max is the RF system. So making sure that the software, everything from making sure the radio is sending the right signals, to making sure that we correct if something goes wrong, to making sure that the data that we send is actually like the data that we need to do different operations, like send a command or receive some telemetry. And so Max and I have different roles, but we're on the same wavelength for the RF. And yeah, happy to talk about what we've been doing recently.
Super cool. So as a quick recap, we just completed a pretty big milestone. We did an end-to-end RF test where basically a signal, and correct me if I'm wrong, but my understanding is we sent a signal through our entire radio system from the ground to the spacecraft, through the flight computer, and then back again, back to the ground for the first time. Like the whole loop integrated, and it all worked exactly as it was supposed to, right, Max?
Everything always works exactly as it's supposed to.
No,
here
nothing,
at AstroForge.
No lessons learned, no major crap ups. It all worked perfectly the first time around.
We had a lot of fun setting it up, and there were, of course, a lot of issues. Some of them we knew about going in. Some of them we actually discovered because of the test environment that we were in. So it was a lot of lessons learned. Yeah, we got a lot of really good data points out of that. One of which was, and we'll get into the exacts about it, but you're not actually too far off. And I think legally what you said is all true.
Legally.
Chris, by the letter, yeah.
Good,
yeah.
Great. Chris, I mean, any rebuttals on your side? Did everything go great the first time around? Was it a harrowing experience?
Well, legally, no. I would say that the. No, I think we were all left the test very happy with the test, but the test plan and the test outcomes were not the same. And I think that's the thing that's interesting, and actually is part of why we run a test. If every test plan was exactly what the test outcomes were, then tests wouldn't have value, right?
And you probably shouldn't have even done the test in the first place because you already would have known. Well, okay, wait.
Well, that's actually... Oh, sorry.
Well, let me back up. That's an interesting thought, but I also just want to know, how many times did you say to each other during this process, well, this is why you test?
I think I'm the only one who says that.
You say it, and then Max rolls his eyes.
Yeah,
I'm not sure.
Let's say, like, let's say, for instance, and I'll maybe be spoiling a little bit here, right? So there's one point where we started transmitting, and then we realized that the crosstalk from our transmit and our receive was much stronger than we thought it would be. Which every time you transmit and you've got a receiver, it's picking up signals. Some of those signals that can get picked up are the same signals you're trying to transmit, and you, of course, don't want that. And when something like that happens, when we realize that, I think other people are like, "Oh, that's like really high, crosstalk." And then, I don't know why, but like I'll say something like, "That's why we test," and then it's a little bit like, everyone's like, so it's but that is why we test. Um, and I think, yeah, I think that might be a good place to start if we wanted to talk about the
Yeah.
differences.
Yeah, let's jump right in.
Okay, so and Max knows way more about this than I do. But just to talk about like what we were trying to do, and then Max could maybe explain like where we went wrong, which is like what we're trying to do at a really high level is in our HITL lab, which we have really close to over here all the time.
HITL stands for
Hardware in the loop. So we do testing with hardware in the loop. Hardware in the loop, the implication is like there's software running and then there's hardware in the loop. But it also means a lot of our avionics get tested.
If you've ever watched a rocket factory or company tour and they have a mocket or a flat sat or any sort of thing like that, that is basically we here at AstroForge we call it a HITL, horizontal integrated hardware. What is it?
Hardware in the loop.
Horizontal integrated total loop. Yeah, that's what it. Yeah.
Yeah, hardware integrated, totally legal, as Max said earlier.
All right, hardware.
And we've got
Hardware in the loop. Got it.
And it's hardware in the loop. It does happen to be horizontal in our case. But pretty much every day, what we do is we have software that kind of pulls whatever the latest code is, and then starts transmitting and receiving, sends some commands, receives some commands. It actually takes a picture of like the room. Of the HITL room, and then sends it over the radio, but that's all over cables, and the signal never actually goes through the air. So when we had this chamber, we wanted to do at some level like the same thing we do in HITL. One of our tests, same thing we do in HITL, send commands, receive data, but over the air. And then we also really wanted to validate that the models that Max has been working on, that he can talk a lot more about, that like what we're actually seeing in terms of how much we transmit, how much we receive, matches our analysis. And I'll let Max talk about what we observed.
Really quick, you said chamber, and I should point out that if anybody out there on socials has seen our recent postings of the fantastic new anechoic chamber that we have had built, that is the chamber we're talking about. So that chamber is what enabled this test.
Well, actually,
Oh, I
It
just
was
got
a-
welled actually. I just got welled.
exactly.
Yeah.
So here we go.
There
You're
is an
talking to
actually.
engineers here.
That's how I know.
We're in a very similar anechoic chamber up in Anaheim. Great guys who run it. The issue is that it's about 40 minutes away, and we have to transport a lot of expensive hardware. We needed to rent a U-Haul, and not one of the small little, pickup trucks either. It was a full, I think, like 20-foot box U-Haul. And nobody wants to do that, especially at a startup like this where we're testing every day, and every time we push some new code, we want to see it. Well, how does that affect the system? Can't do that if we're having to drive up 40 minutes into Anaheim to test. So the anechoic chamber that we posted on our socials was actually our response to that. Was we want to do this very high intensity repetitive testing in our own facility. How do we enable that? Just build our own.
Heck yeah. Well, I'm glad we did, just because it's a fun thing to photograph. It's also kind of fun to stand in there and just be like, hello? Hello? And then someone like 10 feet away is like, what? And I'm like, okay, that's right. It's RF. It's RF. It's not. Anyways, so please continue. How'd the test go?
Yeah, absolutely. So at a high level, I would call it a success because exactly what you said happened. So we, for some context, these anechoic chambers, and I think your post does a pretty good job of explaining it as well, but if anyone hasn't seen it, they do two things. They block RF from going in and out of the chamber. So, for example, if you walk inside of one, you can't send text messages, you can't send phone calls. That was actually one of the first ways we tested our in-house one. Was Bobby walked in and he tried to send me a Slack and it wouldn't go through. The other thing they do is they prevent reflections off the sides of the chamber. That's what those blue spikes on the edges are for. So a microwave is like half of an anechoic chamber where the walls don't let anything through, or, I mean, they always let a little through, but they only let a safe amount through. Now, the reason a microwave microwaves is because it doesn't have those blue spikes on the edges. So if, not to, raise alarms because it's really not alarming, but if we had a higher power system and we put it into our chamber without any of those spikes on the walls, it would essentially be a microwave.
That's slightly disconcerting, but
a walk-in microwave.
yeah, it's like
exactly
a
what you
walk-in
want.
freezer, but
Yeah,
it's a
opposite.
walk-in microwave. Oh my god. No, but I actually, funnily enough, just recently I forget what I was listening to. I think it was a podcast. Might have been Project Hail Mary because I'm re-listening to the audiobook ahead of the movie. But the wavelength of the RF matters in terms of what it can get through or what it can interact with. So like the grating on the door of the microwave is a certain size, so basically the microwaves can't get through the grating,
That's
which is why you're
exactly
able to
right.
see the light getting through it, but not their microwave because they're at different wavelengths.
Exactly.
So do the blue spikes in our chamber have to be like specific spikes that were tuned for a specific frequency, or is it just sort of a broad spectrum?
That's a good question. So these spikes, how they're manufactured is it's some kind of foam. It's not styrofoam, but it's not too dissimilar from that. And while they're mixing up the goo that becomes these spikes, they load it with carbon. So I'm sure that carbon has a pretty significant effect on what I would call the reflection loss of these spikes. Reflection loss. You want them to be having relatively high reflection loss. But the more important thing that I've noticed through quoting this whole chamber out is the actual geometry of these spikes. So you are correct, actually, in your assumption that the wavelength compared to the size of the spikes matters. It does. Smaller spikes generally get better as you go higher frequency. So our spikes on the back walls and on the top and the bottom and the side walls are, I think, 8 inches long. And those give us fairly good reflection loss. I believe somewhere on the order of 10,000 times. So you send some power at those spikes, 10,000 times less comes back. The ones near the door are smaller, which we did because it makes it easier to get in and out of the chamber. But those spikes have a lot lower reflection loss. Those are closer to 100 times power is lost in those. So the important part about that is we size these spikes so that way these numbers that I promise I'm not pulling them out of my ass. The vendor will give you these data sheets, and what you'll see is that the larger the spike is relative to the wavelength, the higher reflection loss you get. So bigger spikes are better at absorbing low frequencies. Smaller spikes are better at absorbing high frequencies, but at that point, the big spikes are even better. So you kind of get this trade-off with where do we want to put what size spikes?
That's fascinating. I'm so glad I don't have to deal with any of this stuff. I just have to point camera, push button. It's way easier.
Well, you got to be on LinkedIn all day. So.
Oh God, don't remind me. Wait, how do you know I'm on LinkedIn all day?
I was right.
Wait. Cool. Well, let's keep jamming away on some of these questions here about the end-to-end test. Chris, why does this test matter in the context of Deep Space Two's mission? I mean, it's not like we have had issues communicating with the spacecraft in the past, so why do we care?
Well, that's a good question, actually. Like, there are a couple different things we're trying to test for each test, right? And like you said, we've had communication problems both on our last mission and our mission before. Now, communication problems is interesting because while it's still not like completely 100% provable exactly what happened on Odin, our last mission, certainly, like, if your spacecraft, for instance, blows up, then you'll have communication problems.
Right.
If your spacecraft is fine but it can't communicate, you'll observe exactly the same thing and you'll have communication problems. So it's a little bit tough. But of course, we want to make sure that if everything is working, that we have communication problems, that we can communicate as well as we can. So for our mission, there's kind of two things that I think are interesting. One is like, does anything work at all? So can we actually transmit and receive and get everything? That's kind of stuff that we can validate kind of just here with our setup that we run every day. We know that like we're sending at the right frequency, we're receiving at the right frequency. But then I think very interesting in the mission is like when we're very far away with these, I'll call them like, the ground stations we have access to, because there's missions that are hundreds of millions of dollars, billions of dollars that have access to the deep space network. And
yeah,
all
we
these
do
things.
not get to use the Deep Space Network.
Right.
I wish we did. If anyone out there knows anyone at the Deep Space Network, hey, hi, We literally are a company that sends probes to deep space, so that would be really useful and helpful. Turns out, Deep Space Network is like way oversubscribed, and like it's extremely hard to get time on any of their dishes. Which is why it's not like we're not using it because we're like, ah, screw you, NASA. We don't want the DSN. No, we would love to use the DSN. It'd be great if we could use the DSN because the whole ground station part of this equation is a conundrum from what I have been told and what I've read and learned, and it's real hard. And all the ground stations to be on the same page, and you don't know if it's going to be some amateur guy in, east somewhere, or if it's going to be a government organization or what have you. And there's wildly differing levels of proficiency within that band.
But partly because of that, the second thing, so will it work at all? And we've spent a lot of time on that, and that was actually not like that easy, But then like the harder and more interesting and more unique to AstroForge part is we're at some point in the mission supposed to be 20 kilometers away, and we're still supposed to get our data, and we're still supposed to be able to send data. So we need to validate that the models that we have and our understanding of how, like, we believe that the antennas are omni, and that they will have a certain pattern of RF coming out. Do we observe that pattern when we actually transmit? Like, is the power what we'd actually expect, and can we extrapolate? Like, so those are the things, the stuff that Max, much more so than me, has been working on a lot. That's what like the over the air really lets us prove.
And to boil it down even further, all we get out of the over the air, and I say this all, right, as if this isn't a huge, possibly most important piece of our spacecraft,
Right.
is that we're able to test without antenna hats on the antennas. An antenna hat is it's a metal box that slips on top of the antenna, and it has an RF port on the backside, and it lets you transmit out of the antenna, but not into a room, say, full of hardworking AstroForge engineers.
Right.
So what we win out of going to these anechoic chambers, if you remember, the first thing that these do is block signals from coming inside or outside. That's what these get us, is we can sit comfortably outside this chamber and blast as much RF as we want on the inside, and no one's going to get hurt. No one's going to feel bad, right? Everyone's going to be happy.
No one's going to get cooked from the inside out like a hot dog in a microwave. Yeah. Wait, Chris, why are you laughing?
Well, and I don't. You might ask, like, okay, well, it blocks signals coming in and out, right? But how do we like control it and stuff? And so what I was thinking is, and this is not at all. It's just I was remembering this thing that we had to do where there's some holes in the
where the entire freaking room was built, and then somebody, I assume one of you guys, was like, "Hey, we need a hole in the special box."
That was me. I know what he's talking about, but yeah, we need a.
Oh, in our chamber.
Yes.
Oh, yeah.
So in order to control things, right, because I did just say no signals in or out, not super useful if you can't actually tell what's going on inside. So what we do is we cut holes, very small holes, into a sheet of metal and inlay that into the wall of the anechoic chamber. And these holes are small enough that not very much RF can escape. And we also have a lot of other tricks to make sure that the room is metallically fully closed. But all of that aside, yeah, we transmit in and out of these holes just using whatever cables we normally use. So that's how I think that's what you were going to say.
Yeah. And the only reason why I thought it was a little funny is because you just mentioned we sit comfortably outside. Me and a couple other people, it's like, who's going to be right in front of the hole, And so like some of us are like right in front, and it like, I think a little bit of this is like psychological, but there was one point where I think it was Ethan was like, man, my skin feels a little hot. And then he looks at the hole really worried, and then goes, no.
I do remember that.
But we have meters and stuff, by the way, just for people at home. Like we can detect how much, like how intense the signal is that's leaving the holes. And point was it.
But it is a little scary. And sometimes I get a little paranoid, even though I know how well the room we built works. I'm like, man, I am all of 2 feet away from this thing that if I was normally 2 feet away from it would not be good.
Yeah, I mean, I think of it a lot like nuclear radiation. I mean, it's literally radiation. It's electromagnetic radiation.
It's non-ionizing. There is an important difference, though, between that and nuclear radiation. Nuclear radiation is high enough energy that it will like mess up your DNA.
Right.
The worst thing, and correct me if I'm wrong.
It'll make the water molecules in your cells vibrate in a way that you don't want them to.
Yes.
Similar to a microwave.
Exactly.
That's a great way to describe it.
But no, I've spent a non-zero amount of time very near or on top of or directly in front of various high-powered cell antennas or microwave shortwave hop type antennas. Because it turns out when you're at a high point to get a photo of a rocket, oftentimes there's antennas there.
I guess so.
And there
yeah.
have been times where I've been leaving, a location after having sat in front. I'm like, am I sunburned or is it like I
Oh,
can't?
my
Like
Yeah,
I don't
you
know,
don't want to
man.
be chilling in front of the 9-meter
No,
dish.
no, safety first. So at least you guys and us here, at least we have like the appropriate monitoring. I mean,
Yeah.
the whole point to that is I understand the paranoia.
Well, I mean, anything, and I think you are right in one way is that like nuclear radiation, you just don't know how much is around you unless you have the right tool.
Right.
And even though sometimes even though you have the right tool, you're like, do I trust it? That's why you get 2 of them.
Right. Yeah, no, it's just a danger that you have to like a hazard that you have to be aware of that you can't see or feel, or I guess you can kind of taste radiation if it's strong enough. But if you're tasting nuclear radiation, it's probably you probably have bigger things
Might
to worry
taste
about.
like blood, yeah.
Yeah, or I think it just tastes like iron. Is what I've read.
Really?
Yeah, but it's like a metallic taste. Or so I'm told. I've never been to Chernobyl yet. Cool. So what subsystems are involved, like from the ground, the spacecraft? Is it like, I know we used all of the different pieces of the pie, like that's the point of the test, but like, can we run through them a little bit?
We didn't use all the different pieces of the pie, but we did use a lot of them. So the avionics, I mean, I guess it's all technically avionics. So to be a little more specific, our custom boards, I'm sure we've talked about it on this podcast before, but we've spun up 5 different boards in-house to control different aspects of the satellite. Was it 4 or 5 of them were integrated for this test?
One of them was there, but there was nothing like on it. It was a pass through to the other boards.
So we were actively controlling 4 out of 5 of our custom boards to perform this test. A pretty significant portion of what our ground system will look like was in play. So we had this was another reason why we needed the U-Haul, was we had this huge heavy cart full of electronics and like rack mount equipment, most of which is fairly similar to what we'll see at the ground stations that we go out to test in the coming months. Again, because we want to simulate like, okay, these are the radios that they'll have at these ground stations. These are the processing units. How do we control these? Easiest way was to buy our own and bring it there. Not as if we didn't have them already, but that's why we wheeled them out with us. And there was a lot of support hardware and software that needed to go with that. Of course, the software. In order to actually control these boards, we have to have a really good understanding of just one example is like the pins on them. So the way these boards all connect together is through a backplane, which is it's fairly complex is my understanding, but at the end of the day, it's a small amount of control and a lot of different wire routes. I say wires, it's traces, but it's like probably a couple hundred.
Yeah, I mean, in terms of like inputs and outputs, GPIOs and other things, yeah, I think we have more than 100 pins.
Yeah,
that are
and
individual. Yeah.
the thing is that the people who are designing these boards are different from the ones who are writing the software a lot of the time. So a lot of the spin up to this test for the first couple weeks, like T minus 2 weeks, you could call it T minus 3 weeks, was plugging all this stuff in, some of it for the first time, and making sure that the software could even control it. Again, the people who are writing the software definitely had a hand in developing these boards, but there's a lot of decisions that are made to address a specific problem that maybe don't get propagated. This is why we test. So one example this is a really simple example, and if you want to elaborate, Chris, go ahead, but I remember there were some pins that went high or low to control some of the functionality on the radio. And what we found was those pins were actually mapped incorrectly, meaning that the software thought it was turning the radio on and it was sending a command to a specific pin. But somewhere in the line, the pin that did that was moved to a different spot. So we were turning on something completely different than we thought. And again, that's why the software is a huge piece of this, is we actually, for the first time, integrated a lot of our systems. not for the first time, I shouldn't say that, but at this scale, this was a lot of systems that have never seen each other talking to each other
Right.
for the first time. And of course, the RF system. So all of my amplifiers, my antennas, my passive components, and the radios, those have never, until this test or until a couple weeks before this test, hadn't really talked to our custom boards all that much, at least simultaneously. And that's also because there's always other testing going on, right? I can do some specific RF tests on my RF hardware, manually controlling them, sending commands in kind of a stupid way compared to what we have on the spacecraft. But these components, they just float around the lab. They're all undergoing different tests. It was kind of like a nice conjunction of things that all came together for us to see, like, oh, this pin got moved and we only noticed because everything was plugged in simultaneously and we got a glitch.
That's fascinating. My immediate worry would be like, okay, now how do we make sure if any other pin moves, like we know, like
Test the hell out of it.
I get to test more.
yeah.
Yeah.
I mean, but that's a great point. So one of the things we ran into we had some mismappings. We had some mismappings that were software related, where we have this way of generating like a bunch of configs for where the pins are. And maybe we configured, because it's not just the pin too. Like some pins, like Max was saying, are active low, some are active high, some are inputs, but they need to be they're inputs where you want to get the rising edge, like only when something changes do you want to measure. Some you want to only really do something if it's high for a certain amount of time. So there's all sorts of, even those 100 pins, even then there's more configs. Most of them are pretty simple though. They're like on or they're not on. But like a lot of them are not that way. And then so we had to go kind of back and forth a lot. And one of the things that was really cool though is like, then we got to a point where we had all the tools we needed that we could essentially check all the pins via software. And actually, Ethan Long, that was one of the things Ethan Long and I were working on. Ethan, at some point, just took it and ran with it, where now he has a way to check out every time they have a new board, every pin, and he can see, is the actual pin I expect to have voltage across it? Like, is that actually working as expected?
Yeah, that's a huge reason why we do these tests, is because we don't, and I think Chris was saying this, is that we don't only get the results on the checklist out of the test. We also get all of this infrastructure that as a startup, we just haven't needed to create before.
Right.
It's this pin checking tool, right? It's a lot of stuff on my end that, for example, I have a lot of different ways now I can automatically control my hardware, even if it's not on flight software. The only reason I needed to develop that was that we didn't have the tool already and we needed it for the test. So these tests, we come out with a lot more than we are expecting to go in with. Even if sometimes it's not exactly, what we're expecting, which I think would be a good thing to get into. Like Chris was saying, we did not see all of the results that we wanted, even though, again, I'll say it again, by the letter of the law, we transmitted to the satellite and it received it, and the flight computer processed it, and it transmitted stuff back out. What that leaves out is that Chris was discussing, he was mentioning that we have crosstalk between some of our antennas, which is not a killer thing. In fact, we're doing a lot of work right now, and we have multiple solutions in the pipeline for this. But what it means is that it wouldn't be safe to operate the radio in the receive and the transmit mode simultaneously.
Because like the transmitting might blow out the receiver.
Yes, that's right. That wouldn't have happened for this test. We weren't, I'm saying I wasn't sure during the test, but having some time to come back and look at the math again, we were very far away from blowing out the transmitter. We probably could have tried it, and it probably would have been fine.
Sorry,
but
just
a lot of
for blowing out the
probabilities.
receiver, right? Like we almost blew out
Yes,
the receiver.
excuse me.
Okay.
Yeah, blowing out the
Yeah, yeah.
receiver, not the transmitter.
Good
The
catch.
transmitter blowing out the receiver.
Right.
That's what I meant.
Interesting.
Yeah, so where was I? Oh, we had this crosstalk issue, which meant that we didn't feel comfortable simultaneously transmitting and receiving. And personally, this hardware is very expensive. I was so concerned that something would get damaged that in between receiving the signal from the ground and seeing that go into the flight computer, I would actually go into the chamber and disconnect all of the receiving components so that way we could only transmit. And same thing the other way around. While we were receiving, I disconnected all the transmitting components. So we did receive and then transmit, but there was about a 40-minute gap, I would say, between those two events happening, which is, again, that's a reason why we built this chamber in-house, is because these little things, not little, right? But these things that we're not expecting will crop up during an actual full test. And we're like, damn, if only we had, if only this was at home, right?
Right.
Uh,
We have RF chamber at home.
exactly.
RF chamber at home. It's just like a pantry.
One thing, and not to, but as part of, because you were asking originally, like, what are all the different components we hooked up? I think there's also an interesting, and you touched on it briefly, but like, where Max was setting up this whole deck, like on the Hiddle, we have a lot of stuff that's like, we have a power supply hooked up. We're not actually actuating things the way we would in real life, but we also have like the radios like on the table. On the actual thing, and I was shocked by actually how important this was for our test, but like even the position of where the radio is on that little like metal square that we have can make a big difference where the amplifiers are. And so I think that if you had, just something that I was interested in, like all the like if you could briefly talk about that process, because I just as the other side of the avionics stuff.
No one is happy with where anything is on that RF deck. That's what we call that panel that we brought to, and I know you know this. I don't know if you know this, but there's a specific panel of the satellite. It's one of the 6 faces of the cuboid. It's the plus X panel, so that means something to Chris. I don't know how much that means to you.
Look, it's not my first rodeo. I know about
Okay,
I know
I'm
about
sorry.
coordinate systems. Feel free to explain it for the viewers, but I totally know.
And for me as well, to be
In
honest,
my mind, the
because it's
plus
easy
X
to lose
panel
track.
is the top of our satellite, so it's not. It's the panel directly opposite the one that houses our thruster, which is important because I want my RF stuff away from those ions as much as I possibly can. So
Makes
it's on the
sense.
direct opposite side. The layout of those things on that deck, though, is, nobody's happy with it. And that's really what a lot of spacecraft engineering is you're put in this tiny little box with a lot of people who all want to make the best system that they can. And that means making a series of compromises, right? For example, on the first revision, we've gone through a couple of re-layouts of this system, which themselves take 2 or 3 weeks from conception of we have a problem to actually receiving the first testable unit. Our first revision had put our low noise amplifiers, ultra sensitive. They're detecting signals that are, I believe, 10 to the minus 14 watts in power.
Holy
this is
cow.
like, no, 10 to the minus 14 milliwatts. So these are like smaller than picowatts. I checked it on Wikipedia one day. It's like yoctowatts or something.
Femtowatts, yeah.
Well, it's below femto for sure.
That's wild.
These are very, very sensitive devices. And now, this wasn't me. I don't like to say this wasn't me, but a lot of decisions were made before I got here. Someone stuck them right next to the power amplifiers that are outputting at like 35 watts.
Yeah.
They actually operated surprisingly well while they were put next to those power amplifiers, but it was still higher than we want to fly. You would imagine it would be horrible. It was pretty bad, but it wasn't killer. So we rearrange it and we move the low noise amplifiers to the outside of the spacecraft. Well, that comes with its own challenges, right? These things are kind of radiation shielded, but it could always be better. So we build boxes around them. Well, now we got to test the boxes, right? Like Chris was saying, the positioning of these radios, we try and position everything as far away as possible from our low noise amplifiers. And that means that some things are next to each other that I wish they weren't next to each other. For example, one of our power amplifiers does sit next to one of our radios. I'm thinking about how that's going to affect our system. It's not great. It's not terrible. It's okay. We survive it. And we survive it within whatever tolerance the manufacturer gives us on the radio. Could be better, could be worse, So again, these position, and that's not even to talk about like the thermals, right? You don't want to put 2 things that get really hot next to each other. spoiler alert, our power amplifiers are like 30% efficient. So even though they output like 30, 35, 40 watts, they're really dissipating around 90 watts or 100 watts. So they get warm and they get warm fast. So everything kind of has to migrate away from those. But then if we migrate everything away from those, they have to be some within some other constraint. So like Chris was saying, there was a lot of work that we had put into, even in the months before this test, to position these things and make sure that nothing is ever ideal, especially in like systems spacecraft engineering. But things are within tolerance.
I mean,
And that's what we shoot for.
That's all you can ask for, right? I mean, like you were saying, everything is a trade-off. I think of anything with rockets or spacecraft, I'm sure it's the same in like Formula One. Like everything is always a trade-off. Like there's no, I guess it's engineering in general. Like there's always a set of trades. Nothing is going to be, a perfectly spherical cow or whatever it is. Probably butchering that analogy, but okay, let's talk a little bit about just overview. What were we trying to get from the test? What did we get? Are we happy? What's next? Like what's left to validate before launch?
Yeah, we got a couple different things. We were able to test the transmit power out of all of our antennas. That was a big win. Not all of them were within the parameters we were expecting. There were some confounding factors as well. For example, our spacecraft, we hadn't built our harnesses, our cables long enough to talk to the equipment outside of the chamber. So it was kind of closer to the corner than we wanted. And even though these chambers are designed to minimize reflections, minimize things happening, you really want to be dead center. So if there's one thing I could go back, I think this would have improved our trustability of our results a lot, would be getting super long cables. So we could be smack in the middle. Now that's something we can do in our current chamber, which is very exciting.
Heck yeah.
Because we, again, have all the time in the world to do a test in there, say, I think the chamber walls are interfering with this, go to the harness technicians and say, hey, please, can you make this harness a foot longer? And instead of being, driving 40 minutes there, 40 minutes back, we do it 10 minutes. Another couple hours later, it's ready. We also tested the gain on our receive paths. So that's another important test because that tells us how much signal power we improve our incoming signal by. So those were also within our tolerances mostly. Again, there's always an outlier. We had quite a few outliers on these tests spread across them. Our crosstalk test, that was something else. That was an issue that I keep bringing up because it's very fresh and we're very close to solving it right now in the sense of we're finalizing our design. I had thought about that being a problem before that test, but I just didn't have the means to test it because our antennas, if we want to transmit full power, we have to have the hats taken off.
Right.
And there's other ways we can test it. There's a lot of things to test. And if there's something coming up like an over-the-air test, that's the perfect time to test it.
Yeah, that makes sense. So what's left to validate before launch?
Well, again, I keep saying it, definitely this crosstalk stuff. We're going to be manufacturing our new and improved, quote unquote, no, really improved designs within the next couple weeks. So those are going to get bolted on, and then we'll probably be running a very similar test to our over-the-air from a couple weeks ago in our new chamber.
Nice.
So that'll be fun. I still would like to investigate more deeply some of the like signal parameters that we're seeing. There's a lot of non-ideal effects that can go on in between the radio and the antenna, or from the antenna to the radio, that we really just didn't have the time to test over the 3 days in the Anaheim chamber because it's a lot of setup and it's a lot of things going wrong that you don't expect.
Right.
So these are other things that we're actively testing right now. But I mean, yeah, we just need to put a bow on everything, to be honest. Individually, all of our components seem to be working as expected. And if they're not, they're literally out of spec and we send them back to be repaired.
Yeah.
But aside from that, I mean, and tests like this let us get there, is we plug everything in and see what are the cross effects that we weren't expecting.
Yeah, and then maybe one more thing is we are going to do some RF compatibility tests with our ground stations. So we're going to want to have as realistic and as good understanding as we can of what signals we'll actually be sending before we do our compatibility tests and actually plug into the ground systems. We're not going to shoot the signal right at the dish or anything exactly
Right,
like that,
right.
but we're going to go through their kind of receive chain and make sure that we're getting our actual telemetry. Which, if people remember, for Odin, there was a theory at one point, and we did have some issues with some of the ground stations where we just weren't configured properly. So even if Odin was transmitting perfectly, we wouldn't have gotten anything. So that's like one of those last parts we need to do. Just make sure that the ground is also there.
Makes sense. Dot the T's and cross the I's.
Exactly.
Well, I think that will about do us for this episode. Thank you both for being on, Chris. Speaking of putting a bow on things, you're putting a bow on your time here at AstroForge.
Doxed. Whoa.
That's true. Yeah.
What's that like? Did I make you mad? Do you not
No.
like me?
Oh no, I have no problem with you. What do you mean,
Bro? No, seriously, thank you for everything you've done. I'm glad we got you on the pod one more time before
Thank you. It's
before the sun setting.
Yeah, no, it's been good to be here. I am leaving AstroForge, but I'll definitely be watching the launch when it happens, and maybe even doing a little. Hopefully not, because everything will go as expected, but some support as needed if things come up.
Heck yeah.
But yeah, I mean, I think everything is moving in the right direction, so I'm excited.
Heck yeah.
Um,
Well, happy trails and whatever's next, and we'll hopefully get to interact again soon. Also, is there any space tuber reporter or whatever out there you want to say anything to? Because they're probably going to be watching this.
oh, I mean,
You're on the spot.
I guess. I mean, this is actually kind of fun. I didn't even think about this. Honestly, like everybody, like actually, you're one of the people who I used to watch back in the
No,
day.
we're not talking about me. We're not doing that.
No, maybe we will really quick. So, like, I used to watch NASA Space Flight, where Jack used to work, and I also watched Tim Dodd, like Everyday Astronaut and stuff. And I started out, I mean, when I was in college, I was just like a fan. Like, I would watch like webcasts. I would watch it was pretty early on at that point, but I'd watch like the Star Hopper, like the early Starship stuff. I watched kind of just like Commercial Crew, all this stuff. Like, there's so many things going on. It was a great time when I was in college to be interested in space. And Anthony Colangelo, Main Engine Cutoff. So all these guys actually really improved my interest. And I had this surreal experience if I had the opportunity then to be working on some of the stuff that was in the space news at my last job and here. And I still, am on like Spaceflight Now. I still listen to Main Engine Cutoff. I still watch Everyday Astronaut. And so the stuff of the media too, that's actually one thing like maybe we don't think about enough, where it's like the reason I ended up doing this personally, like the space stuff, is because I had exposure to it from these people. Like, no one in my family or that I know or knew before college did anything with space. I saw stuff on the news, but the way that I actually got to know parts of the industry and have a sense of what I wanted to try to do was because of people like Jack. So thank you for that.
That's the highest praise anybody could give somebody who makes things, is that like, hey, the things you made affected my life positively. So
They really did.
it's awesome.
Still
Heck
do.
yeah. Thanks, man. Max, thank you for being on, good buddy, and thank you for making sure that our radios will work as best we can.
Fingers crossed.
Hey, no, we're not cross. It's just gonna work. It's just gonna work.
No, I have full faith. I'm very excited to watch this thing fly.
Heck yeah. The launch is gonna be awesome when it does. As a reminder, Deep Space 2 is launching with Intuitive Machines 3 later this year. And yeah, I think we'll keep you all posted. If you have any questions, we didn't do mailbag this episode. We didn't have any questions. So if you want mailbag to continue to be a segment, throw your questions in the comments of this video on Twitter. Email them to mailbag@astroforge.com, whatever you want to do. But send in your questions and we'll answer them. Until then, and until you send in more questions, no more podcasts. No, I'm kidding. But I think that's it for this one. Thank you both for being on. We'll see you on the next one.